So, there has been some new research. The good thing is, as you all know, the number of tokens that LLMs can take in is growing. We have models that basically can take in now 10 million tokens, and the labs are working on kind of unlimited token amount models. So that's it. It's great. This might be easier than I thought. So, and when we look at their metrics, number of benchmarks are based on the needle in the haystack benchmarking, where you literally have, a piece of information in the text. You ask a question to find a model to find it, and it's performing better and better. So this is easy. This is probably solving our problem. 10 million tokens. That's around 100 Harry Potter books. You can put them all into context. Needle in a haystack works well. That's it. It's great. So LLM Utopia, you just put everything in context. It returns the results. Everything is done. That's my talk. Thank you. I didn't want to stay between you and a pizza, though. But there is this one thing. There's this interesting research about the context rot. No, it's a wrong photo, sorry. This is the real context rot. So the research behind the context rot was what researchers were trying to do is evaluate performance of different models as the context size increases. And you can see the drop basically, as the tokens, you go over 1,000 tokens, 10,000 tokens, there is a significant drop in performance. So it seems that, although we thought that the LLM will treat the 100 and 100th token the same, it obviously does not. So we do need context engineering. That is good. So I do have a talk.
Can you comment the diagram previously? It's
Yeah.
hard to read.
Yeah, of course.
Why do you have spikes these on the?
I mean, the research, it depends because different models.
Sure.
It depends how they perform. When you put 10 to 10, it's 100 tokens. So between 100 and 1,000, this is where attention is very focused. You don't have. So what is the problem? Is basically as you increase the number of tokens, the number of these pair relationships that attention basically, algorithms, it stretches the attention for the model, and this is why it starts dropping basically over time. Yeah, that is the Levenstein distance on the axis. So I'm not doing the usual apple, not. The y, the axis down is basically the input length. Basically the upper axis is basically average Levenstein distance score, because you're comparing the results you want with the ideal answer to the question. You have basically these are focus problems that yeah, no problem. So then, I do have a talk. This is good, context engineering. I just love these photos. This is amazing. Just this is worthwhile all the AI hype. If they say that there's AI bubble, I just don't trust them. This is, So, but before we talk about it, just a bit about myself. I'm a principal engineering manager in Microsoft. I supported an amazing team developing Context IQ. Some people are here as well. That's great. Previously, I was an engineering manager in Meta, managing React team in London, and done a number of things before as well. Okay, so let's get back to our problem. So what is context engineering? So, context engineering was, the discussion was, as everything nowadays starts on X, of course, or whatever on the internet. Basically, Lutke was sharing this, concept of context engineering. And then, of course, Andrej Karpathy replied with this now fairly well-known, basically already tweet, that context engineering is the delicate art and science of filling context window with just the right amount of information for the next step. And this is like what became, probably closest to the definition to what we're trying to achieve with context engineering as we develop agentic systems. So why does it matter? We already touched based on some of the areas. Context is a finite resource, especially for multi-turn agents. If you have a multi-turn agent, each step in this process will generate more context. As you have the tool calls, and they go back, or you basically search and find more documents, and this is all coming back into the context. And you need to basically manage that resource carefully. large amount of unstructured data shoveled into context does not guarantee better answers, as we saw from the previous research. And there are a number of context problems with large context that were identified. The first one was a context rot. Everyone remembers the amazing photo. The other one is context poisoning. This happens usually when you have a hallucination in a certain step of the agentic workflow, and basically then that hallucination proceeds affecting the performance of the model through the whole process. Content distraction, where you have distracting information in the context. Confusion is when you have conflicting information in the context, and the clash, where you have literally two pieces of information that are saying completely different things in one place. The last concern is, of course, really relevant for everyone paying for AI tokens. As you have more basically context, you pay for more tokens. Your cost, your latencies balloon when you don't manage your context properly. So what it is in more detail, basically, the idea behind context engineering, it is not just prompt engineering. It's not, just the idea how do we tailor the prompt that we are sending to the model so it is easy, giving us the best results. The idea is to build a whole input system for your agentic system that literally has different areas how it receives the context. The main goal behind this is to provide the right knowledge at the right time. So just use the most relevant tokens for each of the requests. The key metric, I would say, is how we optimize the signal-to-noise ratio. So ideally, in each of the steps in your agentic workflow, you will have only the tokens that you need, and you will have none of the tokens that you don't need. That's utopia. You won't get there, but trying to get closest to that state is how you will optimize the performance of the model. And as I said beforehand, we try to treat context as a designed interface for the LLM. So we work through it very thoughtfully, not a dumping ground where we put all the data. What counts as a context? This will be just a quick slide. So it counts, all the inputs to LLM. This is your previous chats, basically your tool outputs, documents that you put in it, but also short and long-term memory that we will be talking about here, and then, different types of received knowledge. So that's a lot, Again, this photo, sorry, I love these things. So basically the idea is, if you think about this, for instance, in a researcher agent, the amount of data that piles up in a context is huge. How do we solve this? So we have a strategy. Our strategy at the moment is focused around 4 steps, and this is something that basically I borrowed this approach to it, but I will go in more detail from LangChain, how they were, thinking about dividing these different steps. First one is you take the context and you want to basically move it out, your context outside of the context window, and store it outside. The first step, how you do it, is you write it, basically. If you have documents that you retrieved, you don't put them back into the context window. You write them into a file, or you keep the references. You just, in the context window, you keep just the summaries. The second problem is how do you select the relevant context for your context window. This goes into retrieval, RAG problems, but also how you're selecting from your short and long-term memory. You should have basically clear process how you do that. Also how you select tools that you use. Compress helps us basically, summarize, improve aggressively the context, and isolation helps us isolate and split different tasks basically to prevent the unnecessary cross, I would say, context poisoning, or we'll say probably more context confusion than the poisoning itself. So, going step by step. Right. What are we writing when we're talking about writing the context? So we are saving all the information that we need to perform the operation outside of the context window. We record the decisions of the previous agentic steps, the conclusions that the agents made, intermediate results, as well as tool outputs for the later steps. This is important, for 2 reasons. We write both the things that we want to preserve for this basically current session of the agent, but we also store things that some of them we want to use later on. And I will talk about this more in the later stages when we talk about long-term memories. So the 2 common mediums we use to write the context are scratchpads and long-term memory. There are more, but I will just cover these 2. So scratchpads, basically temporary storage, usually use it while agent is active in one session, their purpose is to preserve basically the intermediate decisions that you're making. So you either write it, Scratchpad can be represented by a file, can be represented by a state object. You ideally want to structure it so you don't, create just, amorphous if you're creating a larger problem, so you can know which parts of the Scratchpad are relevant for different agents or for different tasks. And, you access to it via simple tools, or just by basically state objects. So we try to keep this as simple as possible, but structured. The next area we are writing in is the long-term memory. So long-term memory persists basically things that you want to live across your agentic lifecycle boundary. Things like, in our case, user preferences, or things you learn about the user, the knowledge of the user. Each of you probably went into ChatGPT, looked into its memory, it, draws some very fun conclusions about ourselves. My kid uses my ChatGPT. There's so many really funny things in there as well. He thinks, I'm probably not going to talk, but it thinks I love K-pop, so I don't, but it doesn't matter. But it makes this really, good conclusions, and this is what long memory is for. Store these stable user preferences, domain facts, synthesized from the interactions. And you can synthesize this basically either in the process of, agent working, or you can do it outside of the agentic workflow. Because if you do it while agent is working, of course you trade off some of the latency. If you do it afterwards, you analyze the logs of your agent, you can still update the knowledge, but maybe it won't be so, in real time. You might lose the opportunity to use this new knowledge in your agentic workflow. As I said, performing it either in main path or outside. And of course, you want to keep them up to date. So when you're updating the memory, you see what is the memory, what is the new conclusion, and you use the LLM to create the new generational version of that. So select. We wrote our context outside, but how do we select the context? So we select context from different sources. It's not just the two sources we talked about, Scratchpad and long-term memory. The main source of context, especially in our case, me coming from Microsoft / big tech / enterprise companies, it comes from the knowledge bases, from the enterprise data sources. Majority of data that our agents work with do exist. If you're in a Microsoft, you might, your company might have 10 terabytes of data in OneDrive. This is where the data is. If you're asking something about a certain project, this is usually where you want to go and find out the information that people are asking about. You also can ask other tools, basically, to get the knowledge. Key part of selection is how do you rank this knowledge, because you will find a lot of data sources. How do you search for it is the first problem, and in enterprise search, that's quite a non-trivial problem. If you looked into, Google, Google solved the search problem with PageRank ages ago, and then, added knowledge graph and other things to improve it. In enterprise, it becomes much more complex, because you don't just, use the votes that, I would say, between the different sites. You need to understand the domain that you're asking about, so you do need more sophisticated techniques. You employ things like knowledge graph. You, of course, can employ basically vector embeddings, usual RAG, but performance of RAG does drop over time. And you also use keywords in some cases. So all of these things are very important to get the most relevant things selected into context. So as I said, selecting from Scratchpad or short-term memory. So here I put both. Basically, it's fairly simple. You usually go into it and you either ask into a certain area of your scope object what you need, or you would basically scratch the whole Scratchpad into memory if it is some simple system that you're making. I will be talking, as I finish this, of course, theoretical part, I will be talking through you to an example how this is applied in a researcher-like agent in Microsoft ecosystem, and you will see why this system might be a bit over-engineered for normal use cases. Selecting from long-term memory, so these are basically procedural memories. This contains instructions first. So think about your .cursor file, or basically whatever CloudMD. These are the files where you put the instructions. So you want to fetch instructions from there, but also here we store the information about the user. What we know about them, And these things are the key for building a strong agentic experience. This is where you can differentiate from the other systems that don't have this understanding of the user, of their intents. And of course, selecting from the knowledge base. This can be 10, 20 talks just covering these areas, and there are probably thousands on the internet. RAGs, everyone knows about RAGs basically. But we noticed that using just a usual vector embedding RAG, you get decreasing performance as you put more data into it. So in order to improve its performance, you need to understand where the real knowledge boundaries, where the real natural knowledge boundaries for your data things. Because what is very funny, sometimes you will see someone just creating a file, and this file has URLs and descriptions of files, and this performing better than RAG. Because the boundaries are very clear. Each of these documents explains a certain topic. It's really well described, and sometimes that works better than RAG that's not optimized. So understanding the natural knowledge boundaries is really important. For code, it's AST. For different domains, the knowledge boundaries will be different. So as I said, you use hybrid lexical vector and knowledge graph search to achieve optimal performance in the large domains, as we will be talking about. Selecting tools is another area. If you work with agents, you will have a number of tools that you want to work with, basically. And there is a number of researches, especially when the MCPs came out, how the number of tools, if you add the larger number of tools, especially if they're overlapping, that it affects the performance of the model. It's not able to find which tool it should use. So you need to be smart how you do this. Usually people, what they do is you would do something, I'll talk about our example, and this is what we're doing. You will take all the tool descriptions, you will create natural embeddings based on those descriptions, and then you will, for the user intent, for the user query, you will try to match and find are the ones that you should use, and then select a couple of tools that you should use in that case. Embed only those tools, send only those tools to the model, and that gives you much, much better results. Okay, our third step, compressing. This is fairly, I would say it's straightforward. You're trying basically to compress the context. You try to remove the unneeded or duplicated tokens and just keep the ones that are essential and needed for you. So what we do, for instance, if we have large documents that we need to pull into our queries as we are analyzing, we pull in the summaries first, and we pull in the large documents only next steps if we really need them. You sometimes, over time, as your basically amount of context increases, you will also start pruning the last elements of this run if you don't need them, especially the tool results are the ones that become stale the fastest. And you also summarize sometimes some of the older steps to keep the context window focused. And the last step in our strategy is isolate. So this is especially important in multi-agentic systems, but multi-agentic systems, work in some cases, don't work in other cases. I'm certain, even during the previous talks, you heard about, for some areas, when you do need to share the context, like if you're basically writing a monolith code, if you try to, in that one file, try to span a couple of agents to do the same job or try to divide it between them, you will get into a problem because they will get into this could get into a split brain situation where one agent wants to change one thing in a certain way, another one in another way. If you don't share the context, you get, suboptimal results. However, there are areas where you can naturally divide this and you don't have a problem like that. Or there are areas where you can compensate for it by sharing some of the data and isolating where it is needed. So this isolation enables you to share, again, minimal amount of set of data into the agent, but it does introduce a trade-off that you might, if you parallelize this very heavily, you might use more tokens. So putting it all into practice. As you know, coming from Microsoft, there are a lot of NDAs, so I won't be able to tell you about the tools we are using internally that are not public. So I will give you an example of creating a research-like tool, basically a research-like agent within Microsoft that is very similar to the research agent that is there. So the first problem is when you think about researcher in Copilot, what you're doing is you're coming into this large company, you have huge amount of data, about number of projects from number of different divisions. And people usually use research agent to understand a certain area. They're coming into a project and they want to understand, they get a summary of that project, or they want to get a financial research done about something. They want to get a financial analysis of a certain product. So the first step for the agent is to understand the intent, of course. The second step, kind of after it's kind of I might talk about this broadly and then I'll go into more detail. So you need to understand the task at hand. You need to grasp the intent behind the keywords. You need to also to assess basically the user data that you can use. And you will have a lot of user data. We will have data about your preferences, projects you're working on, your org chart, who are you working with. All these things will play into the research when you're doing it. We leverage all of that knowledge plus the organizational knowledge, meaning all the documents, meetings, basically calendars, emails into it. And you also, in addition to all of that, you can use various tools, either M365 tools, like Excel for financial analysis that I was mentioning, or tools, for instance, if you don't need to do complex math, you don't want to leave it to LLM, you have tools that you invoke for linear algebra or whatever you want to do. So how does it do it? Basically, it uses this usual, I would say, research loop. The first phase is the planning phase. You analyze the user question, you determine the objectives, and you ask the clarifying questions to solidify those objectives. So after you get the answers to the questions, you again redo the kind of the full, kind of a set of planning and create the final first version of the plan. Then you go into the iterative research phase. It goes into three steps. Reasoning, what specific questions in this problem you're trying to address in this step. Retrieving the data from the enterprise, in our case, mostly, sometimes from the web as well. You review the findings, you see if there are more questions that you need to ask, and then you go through this process again. All the way until, the answer from the LLM results in you needing to do more calls to find basically the truth. After you see that there are no more requirements for getting more calls, you go into synthesis phase and you consolidate all the collected evidence into one coherent report or an answer. So this is just a quick set of sources for Microsoft Deep Research Agent. As I said, there are instructions and query. Basically, so instructions are the system instructions that you have in your system. So this can be your system prompt, but it can be also different prompts for different tools. And there are a number of things that go into the instructions. Query is the user query. And then you have session, as I said, and personal memory. So this is basically the chat history, the state object, the personalization store that will know your preferences, but also knowledge about you and the enterprise data around it. So the company, the agent will know basically in the company who are you working with, who is your boss, who are the people you're most often chatting with. And these are the things that all play into understanding which documents might be relevant to you, because all these chats are also sources of data. And then tool, there's a number of tools, as I said, that you can use. So how does this look, basically putting this four-step strategy in practice for the researcher agent? So first, what we are writing is we write the plan. We talked about, first step being the planning. You create a plan, you store it basically into the state object. You also, from each of the steps, as you go through this loop, basically, you store relevant outputs into the state object if there are small conclusions. You don't store always the whole outputs, but you try to store the conclusions of the agent there. If, as I said, you draw important conclusions about the user, or they tell you that they're starting working on some project, you want to store that. You want to know that because that will be helpful when you're. So you store it and you update long-term memory. At the moment we are doing this, right away, not waiting for the consolidation afterwards. And we consolidate it with the old memory as we're writing it, but while in the main loop. So we're not doing it outside of the agent in this case. So you wrote all of this data. Now you need to select what is relevant, basically, for your next step. You select, both from the current researcher plan, kind of from the state object that you sometimes after the review will update, or you select the data from the long-term memory about the user, which is what we talked about, or pre-selected tools that you realize will be useful, but just for this step. This is important. We use the tool basically on each of the steps. So we know what is the intent for this step, and we try to find the tools that are relevant. You have a couple of search tools, you have different other tools that you use, and we try to always select it in each step which tools should be attached to the LLM call in this moment to minimize the tool confusion. And then, of course, select relevant user documents, emails, events. You cannot imagine how much data there is. And the internal store that we use, of course, uses a graph-like structure behind it. I cannot name it, I cannot tell it. We compress the data then, kind of over time. As you're going through the process, we have noticed that, when we get to 40% of the context window or a bit more, that performance of the model starts dropping. So we try to compress before that, if we can. Extract the key information. However, it is important that we don't lose the information. So we are okay with going over 40% if it cannot be compressed. So that is important. That is an important trade-off to keep in mind. Saves us money as well. Although we are running mostly on our infrastructure, it's still cross-charged. And then isolate. We execute basically coding agents in sandbox. For instance, if you have a coding task, you need to do something complex. It will do it in a sandbox. It won't return all the output of the console back. It will not be, sharing these things back with the models because it's not so useful. It will be targeted. If there is an error, for instance, if you're looking for a document and there is a 401, it won't return a 401. It will just say, I cannot get this document, go forward. So you don't have these artifacts that can confuse it for some reason. All of these things are common sense, but just wanted to, explain how they are put together in this case. So what were the results? You can definitely see a huge difference between the I would say plain chat, which is not a researcher-based agent, and the researcher-based agent. You have, with strong context management and personalization, you get much more relevant results. It completes complex research tasks, and that is mostly because it starts with a plan. Basically, that is what keeps it on the track for a longer time. And of course, the newer models can run for longer times as well. The accuracy of the answer is much better, and you also have citations. So each of these basically references has citations, so you can find it. It's a fairly usual thing. A lot of people have seen it in the ChatGPT Researcher and other places. So that should be it, am I right? That's our example, and over time, as I usually am, unfortunately. But there is this one, I would say, not contrarian, but more dualistic thing I wanted to talk you through, and something that we learned through the past period of working with LLMs. I don't know how much you read the beta lesson from Rich Sutton. So this is basically a really good, kind of a letter that Rich Sutton, who is one of the prominent AI researchers, has written after 70 years of research in AI. He was working mostly on the vision. So the biggest lesson that can be learned from the 70 years of the research is that generalistic, basically, methods with sufficient compute will give much more effective, and give much better results than specialized methods. This was visible, for instance, in vision, basically recognition. They were starting with recognizing corners and all the kind of specialized models. Over time, when the compute and models got sophisticated enough, today's models don't use any of those things. They're much more general and they perform significantly better. Why I'm sharing this is something that we have seen with models as well. We're building this sophisticated setups to try to work around their current limitations. However, over time, models are getting better. So the main lesson from it is, as we build this context engineering, basically, structure system around it, we try to add structure only when it is needed. And we try to create a structure in a way that it can be easily removed or modified. Because as the new models come, the structure will change, might become irrelevant. You will need to change it. We try, when we work with model, we don't try to teach it about doing all these steps as I was telling. We try to incentivize it to achieve a goal and then work backwards wherever it's possible, and only teach it if it cannot perform when you incentivize it. And your context engineering strategy will stay relevant if basically, and only if you adapt through the models as they change. Something that worked for the current model, one generation of models, is not necessarily going to work really well. It might be just hampering the new generation of models. So that was it. Thank you very much. The QR code has the reference materials and the research if you want to find it, so scan it. That's useful. Thanks. Hope this was useful.